तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome everybody to the lectures on computer graphics. We are in the process of discussing different methods of visible surface detection or algorithms for VSD as it is popularly called. And in the last lecture we had seen the concepts of coherence properties which are used in the VSD algorithms, and also we had discussed about back face removal or back face culling. In fact, we are in the process of back face culling, where we found out that the dot product of the two vectors, when it is positive, then it is a back face, which basically means that when you are looking along the positive z direction, then you look into the z components of the direction cosines of the surface normal of the polygon or the face, and look at the sign of that z of the direction cosines and see if that sign is positive, then it is a back face, otherwise it is a front face which you have to shade. So, the concept of the back face culling or back face detection is used as a preprocessor or a front end processing or a front part of the algorithm for any of the VSD algorithms. In fact, you have to use back faces, because we had seen that with an example in the last lecture, that it helps you to remove approximately about 50% of the faces. And if you are able to do that, your computational burden in terms of drawing the polygons which are not to be seen by the viewer is appreciably reduced. You will have the overhead to draw polygons which are at the back of the object and not visible to the user, and if you need to do that, then you will overload the system with lots of extra computations which are unnecessary or redundant. So, enforced back face culling, if you have a simple algorithm, use that, remove those back faces from the list, do not render them at all and show it to the user, only draw the faces which are fully or partly visible. So, coming back to the exact point in back face culling or back face removal, at the end of the last lecture, the computation involves the computing the surface normal of the polygon, and that too within that surface normal the direction cosines of the z component of the direction cosines are important, and if you get that, then it is easy and straightforward for you to find out whether it is a back face or not. So, coming back to the slide which we had seen in the last lecture, is the problem was to how to get the normal vector n for a 3D surface of a polygon. So, assuming that the polygon is represented by a list of vertices or edges in a planar surface, and there are two such edges or the polygons which are given, the P and Q, which we visualize as two 3D vectors, and if you take the cross product of these two 3D vectors, you are going to get a vector R, which is of course going to be definitely the normal to the polygon, because it will be normal to the plane on which P and Q rise, and of course the phi is important, because greater the phi, greater you get the magnitude of R and things like that. But the choice of the sequence of these two vectors P and Q is very important, because if you take the cross product in the reverse order, that means you take Q cross P, you will land up with the normal as minus R. And is it important? Yes, it is, because the order of vertices for the calculation of the n, because the order of vertices will dictate whether you are going to take P cross Q or Q cross P, because you will choose any arbitrary two edges of the polygon out of a set of n m different vertices. Let us say you can visualize small n to be number of vertices or m to be the number of vertices, because capital N is what we have used for the the normal vector. In this case, you can use r or n, they are the same. And we talk of the front side and the back side of a surface. Now, we should not confuse this with the back face we are talking of in respect to back face culling. Back face culling we meant by always the front side of a surface, but whether it is visible to you or not. Now, remember here when you talk of the back face, when you talk of the back face of a particular polygon, a set of polygons form a polyhedron which enclose a solid. So, if you take a particular polygon which is lying on the surface of a solid, let us say this one, then it will always have a frontal and a back side which will never be visible to the viewer, because that is inside the object. A solid object is bounded. Okay. Of course, it could be hollow, but visualize a solid cube and visualize one such side of it, okay, or one face of it, or one polygon of it. Okay, or a quadrilateral or a square in this particular case. That square will have a frontal face which will be on the outside of the solid object, which may be visible to the user or not, depending upon the location of the side with respect to the viewer or viewer with respect to the side. But that surface will have an inside part which we will call the non-frontal or the back face of it, which will always be invisible. So, a polygon will always have a frontal side and a back side of it. Always a front and a back, that back is inside, this back side is inside of the cube, let us say, or a solid object which you have, and you have a frontal side which will be visible and the back side which will not be visible at all. So, we need to find out and compute the n which is coming out of the frontal face, not coming out of the back side face. Otherwise, you will be computing the wrong direction cosines of the surface normal. I hope I am able to give you the visualization. A better visualization comes on from the slide which we see here. Let us say, if you see this particular 3-dimensional rectangle, of course, it is a plane in 2D, all right, but assume this to be brighter side. Why do I say it is a brighter side? Well, this is the outside part of the solid object which is visible to the viewer, and I will say this is a brighter side based on a particular condition. What condition do I impose here? This was not talked about in the previous lecture. Okay. I say I take the order of the vertices in such a manner such that my edges which form the vectors of the polygon, as shown here by the arrows, go in a counter-clockwise arrangement. Basically, it means I take the vertices of this polygon in a counter-clockwise arrangement and order, and when I do that, I will say I am looking into the brighter side or the facing side of the polygon. Now, there is a reverse side of this as well. The reverse side, if I turn the polygon, where the reverse side of the opposite of the brighter side is visible to you, this is what I will call as the darker side. I will not call it on front or back anymore, we will say it is a brighter or the darker side. This darker side is inside the object and it will never be visible. So, I paint it with a color which is non-bright or dark, and if you see the order of the polygons are clockwise, because that is what you will see. If you see from this polygon from the darker side, which is the opposite to the brighter side, this was the brighter side, and I am asking you to look from the other side of this polygonal face, which will be appearing like this, the darker side, you see that the vertices, okay, or the edges appear in a clockwise arrangement. So, that is what I say, that in a particular surface there will be a brighter side and a darker side. A brighter side is the one which you will always be able to see, depending upon, of course, whether it is a back face or a front, that is okay, depending upon with respect to the viewer position, but there will be a darker side which will be inside the object always, and it will never be visible, because it will be always enclosed by other parts. So, why we are talking about this, the brighter and the darker side? Because we want to compute the n very accurately, such that it is coming out of the brighter side, not getting into the brighter side and coming out of the darker side. So, that are very important here. If you look back, we are looking into this P cross Q, which will give this R rather than a minus R, which could be accidentally obtained by Q cross P. To avoid this accidents in terms of the order, we say whether we should take P cross Q or Q cross P, because given to arbitrary vectors you will not know what is the correct face in terms of a brighter or darker side. We follow the following notation, that the brighter side of a face is visible when we are seeing the face and take the vertices in a counter-clockwise arrangement. If you, and the reverse side will be clockwise. So, that means if you take the clockwise arrangements of pixels, you are basically looking into the darker side, and if you are looking if you are taking the arrangement in a counterclockwise arrangement, it is a brighter side. So, henceforth when you make the vertex table or the edge list or the polygon surface table and also store the corresponding vertices or the edges inside, you must be very careful in the sequencing of the corresponding vertices or edges of the polygon, because you must store it in a counterclockwise arrangement to show that that is the brighter side which you are seeing. Accidentally, if you store the darker side, the algorithm will reverse it and take the counterclockwise arrangement and make the darker side brighter, which will cause confusions for you. Okay. So, this is what I meant by the brighter and the darker side, when you need to take the vertices and hence the edges in a counterclockwise arrangement to see the brighter visible part of the surface. Then of course, depending on the end, that brighter side may be a frontal face or a back face, which is involved in the back face culling or back face removal algorithm. That is fine, that is the main part, but here we are bothered about to know which is the correct order of the sequencing of the vertices or edges of a polygon to compute the n with respect to the brighter side which will be visible, not the darker side which is inside the polyhedron as inside the object, which will never be visible under any circumstances. It is something like if you take the surface of a ball, football, which is a sphere, a very good example. That surface has an inside the ball itself, we have a surface which will never be visible unless you tear the ball open, tear the leather of the ball open, it will never be visible, always the outside surface of the ball or the sphere will be visible to you. The inside part of the polygon, inside part of the surface will never be visible, that is the darker side which you talk about. Light never enters there, the light always come and hits the brighter side, and that could be a front face or a back face which will be used. So, I hope the concept which I am repeating several times is clear to you now, that to compute this n, we compute the n with respect to the brighter side, and that is done by taking the order of the vertices must be taken counterclockwise for the brighter side. Let us illustrate with the help of a case of a cube. Okay. This is what we call as the exterior faces of a cube. What I have done is, I have taken the 3 visible parts or faces of a cube which are visible to you, and these are the brighter sides of the faces of the cube. These are the 3 polygons, the 3 rectangles for you, and the surface normals are shown with respect to the brighter side. Remember, there is a darker side of these faces which you could have taken if you had taken the order of the vertices in a clockwise arrangement. If you go and try to look inside, you will find that this order will appear clockwise with respect to the darker face, whereas with the brighter face, it will if you take counterclockwise, you are actually looking into a brighter side, and this is how you complete the surface normal, which will always appear to be coming out. If you now take any 2 orthogonal vectors p and q and see, then you try to take a cross product of that, you will see that you will get this n which is marked for the respective polygons. So, this is how you compute the n. You do not take 2 arbitrary vectors, you basically take an order and then compute. Okay. So, we need to have a formula where we just do not take 2 arbitrary vectors, but you need to compute a normal based on all the vertices, because you could accidentally pick up 2 vectors which are parallel vectors, and then you cannot compute the cross product of 2 parallel vectors. Okay. So, you can choose any 2 vectors typically of edges to obtain the normal to a surface, you can do that, but there will be lot of risks. Can you think of any risk in such a case if you randomly choose any 2 vectors? As I said before, p cross q, after the counterclockwise arrangements is done, somebody can say, okay, I will just use 2 vectors, any 2 arbitrary vectors p cross q in that sequence after it is arranged in a counterclockwise arrangements. Yes, you can do that and still obtain n on the brighter with respect to the brighter side of the face, and then check whether that brighter side is becoming a back face or not, that is fine. But is there any risk if you randomly choose any 2 vectors p cross q? There is a risk. If you think and you are able to visualize, the first and important problem is very easy to visualize. If those p and q are accidentally parallel vectors, like the case in the previous one here. Now, if you can choose in any face 2 parallel vectors p and q, and you know when 2 parallel vectors are chosen, the angle phi is equal to 0, then of course, you will the normal product itself will be 0, you cannot obtain that. What do you do? Can you think of a situation, then of course, you choose non-parallel vectors, one might start. Still, do you think will there be any risk in choosing? Now, there will be risk, because even if they are non-parallel, if they are accidentally very close to becoming parallel, that means that phi angle between the two vectors p and q which you are choosing, they should be preferably wide apart, much larger, but accidentally if they are very close, if not 0, if a small value, what will this will result in is a computation of a value r or the normal n of the polygon, which will be very small in terms of its magnitude, and I would like to avoid that. Small is not a problem in a computer, all right, but is a too small number is a problem. I would like to lead with larger numbers, where accidentally I would not allow numerical errors to creep in terms of truncation and round off. Okay, I would like, if possible, like to have larger values to play with, even if the computational time could be larger, because choice keep looking for two vectors which are not only non-parallel, but not close to becoming parallel also will become additional computational burden for me if I have to keep choosing pairs out of n different vertices or n different edges. Okay. So, I would like to avoid this computational burden and look into a formula which will handle all cases of parallel or not. In fact, it should take all n edges or vertices into account and come up with a formula which will give me the n, rather than keep choosing vertices on and then edges which are not parallel, but almost orthogonal if preferable. Okay. So, let us look at a, yes, there is a problem. So, better solution to obtain the direction cosines of n is this. We assume that there are small n vertices of a polygon, capital N is the direction is the normal to the plane of the polygon, and there are n vertices of the polygon. The xi, yi, zi are the coordinates of the ith vertex, and I keeps running from 1 to n as given the left hand side here. I am reading here. Assume small n vertices of the polygon, and each vertex has coordinates xi, yi, zi, because it is a plane in 3D. Vertices have 3D coordinates xi, yi, zi. I runs 1 from n to 1 to n, or 0 to n minus 1, because there are n vertices of the polygon. If that is given to us, you compute these three coefficients a, b, c. Are you able to recognize these expressions? I think we have got these expressions somewhere earlier in a previous class. Can you guess where you have got this expression? If you think carefully, we got exactly the same expression to compute the surface normal given n set of vertices earlier, but at that point of course time I did not talk about all this logic about direction cosines by picking up any two vertices arbitrarily and then the brighter and cider phase, because those are related to the visible surface detection algorithms. But these are the direction cosines. If you remember, these expressions is what we got earlier. J is equal to I plus 1 when I is equal to n. Of course, we are talking that j is equal to 1, that is, you come back to the first vertex, and that is what you do to compute the surface normal. Okay. So, this is the expression which we have. We know how to compute the surface normal, and to throw some more light now on these expressions, let us go through a little bit fast. Take the expression of C. This we also did in the last class, and we break open that expression and took the case for a triangle, and you can relate that to one property of the 2D polygon xy plane. In fact, we did it for a triangle, and we can also verify for any polygon that the A, B and C also describe the projection of the surface of the polygon on the respective coordinate planes yz, zx and xy planes. That means, the A, B, C are related to the projection. Remember, the polygon is a 3D plane. So, you project it either on the xy plane or yz or zx planes, the three orthogonal axes, that means perpendicular to one of these axes, the three orthogonal axes. So, projected on one of the planes, and you will find that the projected plane will only have two out of the three coordinates, either you are throwing out z, x or y. So, that is what you get with the formula A, B, C. They also describe the projection surface of the polygon on the respective yz, that is, for A you have y and z coordinates, for B you have z and x, and for C you have x and y. So, if A is the total area of the polygon, this is a new concept which you can keep in mind, then the projected areas of the polygon on the respective orthogonal planes are that the area will be A by 2. When you note the formula of the A, which you have seen here, this is this A, B and C, which you compute by these three summation of the product terms expressions, sum of product terms, and the area, the projected area on the yz plane is this A divided by 2, projected area on the xy plane is B by 2, projected area on the xy plane is C by 2. That means, the A, B, C are nothing but, you can also visualize them, they are twice the respective projected areas on the respective planes. cosines. When A is the direction x component of the direction cosine, if I repeat, if A, that coefficients ABC is what you are computing, small ABC, you are computing as the direction cosines of the surface normal to the polygon. A is the x component of the direction cosine, B is the y component of the direction cosine, C is the z component of the direction cosine. Of course, that C is very important for back face culling, I do agree, okay, that you all know. But if you look at A only, let us say to start with, A is the x component of the direction cosine of the surface normal, it is twice the area, it is double of the area which will be obtained by projecting this 3D polygon on the YZ plane. Project the polygon onto the YZ plane, compute the area, that area will be the area which you will get double that area, you will get the x component of the direction cosine. It is proportional to the x component of the direction cosine. So, A is twice that area on the YZ plane, B is the y component of direction cosine. So, it should be twice the area of the projected of the polygon projected on the xz plane. Similarly, if C is the z component of the direction cosines of the surface normal, as if you can see carefully here on the slide, if C is the z component of the direction cosine of the surface normal, then that is twice AXY, that is twice the area projected of the polygon onto the XY plane. So, remember these important relations and you can test it with a simple triangle. So, if the surface normal computed by the above three coefficients, by the above formulas, we have seen the formulas of ABC, they appears to point outwards, it facing towards the viewer, and the edges of the polygon appear to be drawn counterclockwise. This we have seen what you mean by a back face, front brighter face and a darker face. So, I repeat again, the surface normal point to appears to be pointing outwards from the face, facing towards the viewer, the edges of the polygon appears to be drawn counterclockwise. That is what is the situation which we know, and the polygon is a back face, you need to just compute the C, check its sign, if it is a positive, then the polygon is in a back face. Okay. So, this is simple. So, you do not need to, in fact, when you are testing a back face, I did mention sometime earlier that you do not need to compute the x and y components of the direction cosines. You do not need to compute the x and y components of the direction cosines, you just need to compute the C, which is the z component of the direction cosines, check its sign, and that is what you will get as your back face or not. C is positive for a back face provided you are looking in the positive z direction. If your view direction is negative, you have to just do the opposite. If you look back to the slide, is a small note here which you can make, that if, which is flashing on your screen, which reads, if the view direction is along the negative z direction, the above condition becomes C negative, less than equal to 0. Okay. So, it depends upon whether you are looking along the positive z direction or negative z direction. You are checking the sign of the C to check whether it is a back face. The brighter side always could be a frontal face or a back face, that is true. Never we bother about the darker side, and we have computed this surface normal with the direction cosines n by taking this clockwise counterclockwise arrangement, and we are assuming that this n is coming out from the brighter side which may be visible, brighter side of the polygonal face. Now, you need to compute only the C, that is the z component of the direction cosines, check its sign. If the view direction is along 0 0 z, positive z direction, check if the sign of that z component of the direction cosine, that is C, is positive or not. If you are looking along negative z direction, you need to check, what you need to check, if that sign is negative or not. So, that is what you look back, just be careful that the first condition holds good, that the polygon is a back face if C is positive, if you are looking along positive z direction. But remember, if your algorithm or situation demands that if the view direction is along the negative z direction, then the above condition becomes C less than 0. So, I hope this condition is clear, and then we move on to the next topic. But let us look into drawbacks of back face culling. We talked about back face culling. The main idea of back face culling is to know whether there are some polygon is a back face or not, and it has certain, it is good. The computations are very simple, you just need to compute the C, check its sign, that is all you have to do to compute to know, you do not need all the components of the surface normal. and to compute to know whether it is a back face, just compute the C. But the back face culling can do certain things, it cannot do certain things. Let us look at them. Partially hidden faces cannot be determined by this method. This is the first drawback of back face culling. Drawback in the sense that it is not suited for this task. If you look at this particular truncated solid, truncated cube I should say, of course, there are a few faces at the bottom and to the left, and of course, the back faces, two of them which are not visible. And there is a face on the top and the front left and the front right. There are three of these white polygons which are visible to you, that is absolutely not a problem. And of course, there are a few faces on the bottom of the solid to the left back side which are not visible. But look at that part of that solid which is partly visible. You cannot tell using back face culling whether that face is completely visible or it is partly occluded. You can actually only say whether it is a front or a back. Whether it is partly visible or not, a situation like this, you can say it is a front face, but there is something like this here which also say that this is a front face, but it cannot compare two different surfaces and tell you whether a surface is partly or completely visible. That is the key essence of VSD algorithms, or visible surfaces. So, back face culling can't do that, but it only helps you to, still it helps you to throw out 50%, about 50% of the polygon face and say that is back faces. You never compute these normals and do any more processing. You do not use these polygons to compare depths to finding out partially occluded or occluding surfaces. You never do that. So, that is done by VSD, but you always use back faces, and you know that you do not try to find out partially hidden faces using back face, because that cannot be done by back face culling. It is not useful for advanced concepts of visible surface detection algorithms or illumination and shading algorithms which involves ray tracing, photometry or radiosity. When we talk of ray tracing later on, in the future classes, we will see in ray tracing, radiosity, photometry, why this back face culling does not play a significant role. That is later on. However, we move forward to VSD algorithms with the note about back face culling, that this is still a very useful pre-processing step, as almost 50% of the surfaces are eliminated by this method. I told you about this earlier to you already, that the back face culling is a method by which you eliminate a lot of faces. Typically, on an average case, about 50% of the faces which will never be visible to the user based on a certain viewing geometry are thrown out by back face culling, and hence it is always used as a pre-processing tool before applying any VSD algorithms or illumination and shading algorithm. Remember, I talked of this in the earlier class, that we are in the almost last stage of the viewing pipeline. Before mapping into the viewport the polygons which will be shaded and rendered, we are throwing out the few back faces, we are finding out the frontal faces, we are also finding out the part of the occluded faces which are visible to us, and then of course, we have to compute the illumination shading in the next chapter or the next section of the class. This all has to be done before actually drawing the picture on a particular viewport. The last stage of the viewing pipeline is what we are here, and here we are involved in visible surface detection, but applying any visible surface detections, we have given a few list of those in the last class. We will continue to discuss that in the class today, a few of those algorithms, one of them today and more so in the future classes, but always you must keep in mind back face culling has to be done. It must be done, or it has been done before I apply any VSD algorithm, because the back face culling will throw out a few of those faces which are back face and will not be involved in the computations of VSD. So, and that helps to throw out 50% on an average case the number of polygons, and you can now visualize the speed up which you will get in the future algorithms of VSD and rendering, if 50% of those back faces are thrown out by back face culling. So, remember this point, that this back face culling, in spite of having its drawbacks, it is a very simple computation. Direction cosines, z component of the direction cosines of the surface normal has to be computed, check the sign, depending upon that identify it is a back face or not, and then move forwards towards VSD. Remember, it has its drawbacks, but in spite of all these drawbacks, this is still a very useful pre-processing step, as almost 50% of the surfaces are eliminated. So, we will use back face culling, then move over to visible surface detection algorithm, which we will talk next. And the first one in the list which we are going to start today to discuss about VSD algorithms after backface culling is called the depth buffer or Z buffered algorithm. Let us look at this slide. This is what we have as a slide for the depth buffer or the Z buffered algorithm, where we see that we are seeing through a window a set of 3 polygons which are visible, and one is obscuring the other. They are not separated out. They may be separated out, all right, but in this case they are not. And we are talking of a, let us talk even orthogonal projection, but the same is true for perspective projection. But at this point of time, again I bring in the concept that we are in the end of the 3D viewing pipeline, normalizing transformation is done, clipping is done, scaling and zooming to bring everything under the canonical view volume. We also do the transformation matrix, which will transform our perspective projection canonical view volume, the pyramidal structure, into a rectangular parallelepiped in a canonical view volume. So, everything is orthographic right now. The projection transform is also handled under the special case of orthographic now, and within the orthographic projections all rays are parallel and moving towards a certain center of projection which is at infinity. Okay, that is what the rays are going, okay, from the object. So, this is the case which we have seen here. So, the rays will be coming out of that object and intersecting the projection plane, this rectangle image of the projection plane here, and is moving towards the center of projection in 3D. And as you can see, if there is an obscure or an overlap for a particular ray, we need to find out which of these 3 surfaces at a particular point is facing to you. So, that will tell you which is a frontal face, which is partly occluded first and which is partially occluded second. Now, this is an example of only 3 polygons. I would like you to imagine, let us say in addition to 3 you have many other polygons, say 10 of them or 100 of them or even more than that. Okay, visualize a few hundred to a few thousand polygons, and one is obscuring the other and so on as you go, and at any point of time in an image plane you will be able to see one of those polygons, and you have to find out which of that polygon is in front of you based on a certain ray which is going. Or if you take, of course, the ray casting method is more suited for this task, but in depth buffer also we will see we have to compare the depths of these 3 polygons at all instants of time based on a certain pixel point, and then find out which is facing to you, which is in the front of you. I did say sometime back in the previous class that visible surface detection is nothing but a 3D sorting algorithm, and the comparison of sorting is done based on depth. Depth is the cue or the key based on which the sorting is done. Any sorting is done with the help of integer values or floating point. You just compare certain values and do a sorting. So, you need to sort these polygons based on depth, and that is why it is called a 3D sorting algorithm. So, let us see how depth buffer works or the Z buffer works, where we have to start to compare the depths of these 3 polygons across and over this image plane. So, we will say that each XYZ point on a polygon surface corresponds to an orthographic projection point XY on the view plane. That is what we have seen. So, if you take any, if you take any XYZ point on a polygon, that corresponds to a particular point XY on this projection plane. That is true for any of these. You can put the line anywhere passing through any of these polygons, or maybe only 1 or 2 or 3, and you will find that that ray which will be passing through a point XYZ on a polygon also intersect the projection plane at a point XY. So, that is what this sentence means, that each XYZ point on a polygon surface corresponds to the orthographic projection point XY on the view plane. This is an interesting, that is why at the end of the viewing pipeline everything is put in orthographic. Why? Orthographic projection is the most simplest form on getting a projection, because if you have a point XYZ in 3D, its corresponding point, projection point on the projection plane can be easily be obtained by just chopping off or throwing out the Z value. XYZ, take out Z, keep the XY values, that is going to give you the point on the projection plane, whereas that is not the simple case in the case of perspective geometry. Perspective geometry you have to use transformation equations and all that. Okay. In this case also you can use, but you can almost visualize that you do not need anything of those in orthographic projection. XYZ point projecting onto a plane, throw off the Z value from the 3D coordinates, take the first 2 components, that is your projection geometry. Keep that in mind, that is why orthographic projection is often used at some point to simplify the calculations. Then at each, the reverse is also true, that at each point x y on the p p is a projection plane. You remember this term hopefully, which we have learned from 3D viewing, pipeline 3D viewing geometry, when we discussed those issues earlier in the previous class. So, at each point x y on the projection plane, object depths have to be compared or are compared by using what we call the z values. So, now if you have say two planes, plane 1 and plane 2, and if I take a projection plane to your right, say at a certain point x y. So, that point x y will correspond to a point x 1 y 1 z 1 or x y z 1 for an image plane, for a polygon plane 1, and for a polygon 2 it will be for a corresponding other point. Okay? It will have another point x y z 2. So, if you have two planes, you have x y z 1 and you have x y z 2. And z buffering or depth sorting is nothing but compare these two values z 1 and z 2, keep comparing them as z 1 and z 2, and that is what you need to do in VSD. So, at each point x y on the projection plane, object depths are compared by using the depth values. In this case, I am showing by hand that there are two polygon surfaces, but you can have more than 2, 3 is already shown in the previous slide, but you have tens of those or hundreds of those, and all those z's are compared, and you need basically a sorting algorithm to arrange this in some ascending or descending order as the case may be required. So, that is what you do for your depth sorting. This is the key idea. Let us look at some of the mathematics involved in comparison of the case. So, assuming normalized coordinates, if you have a z value and assuming that the z value for your set of objects is lying between your front clipping plane and the back clipping plane. You remember these terms when you used in 3D viewing pipeline. So, we are talking of z values in the canonical view volume, normalized coordinate systems 0 to 1 or 0 to certain z max. Okay. Z max could be equal to 1 for your front clipping plane, but it could be anything else. And if that is so, the algorithm uses two buffer areas, okay, or two memory areas, okay, where one is a depth buffer or the z buffer, as the name suggests in terms of the algorithm, which will store, that is used to store the depth value for each x y position as surfaces are processed. So, we are processing polygon by polygon and we are updating the z at a particular value of x y, that is what we do. And there is another buffer called the refresh buffer, which stores the intensity at each point x y. Now, although these two buffers are used, but in terms of VSD algorithm, the depth buffer is the most important part. That is what we will see, because we will keep the computation involved in computing the refresh buffer or the intensity value for the later time when we discuss the illumination and shading algorithms. Okay. So, for the time being, we assume that we have an illumination and shading algorithm which will compute at each point x y on a polygonal plane what is the intensity. That is again a function of the surface normal n, and surface normal n has been used to it was computed earlier when we needed to do a back face. So, we are computing only for frontal faces, not for back faces anymore, and for those frontal faces we sort them based on z, using the z buffer, and compute the intensity and store them in the refresh buffer at that same point of time. The computation involved in the refresh buffer of IXY will not be discussed in the VSD, it will be discussed later on based on the illumination model which we picked up, although it is a significant part of the algorithm, but it does not play any role in terms of comparing z. So, for comparing z of xy or depth buffer is the one which will be used, and we will discuss that. So, coming back to this two concept here, two buffer areas are used. One is called the depth buffer or the z buffer, which stores the depth value for each xy position as surfaces are processed, and another of course is the refresh buffer. Sometimes people call it the intensity buffer also, which stored the intensity value at each position x comma y. Okay. So, remember this, that the z values run from 0 to 1, and there are two buffers which we need, which are used for the algorithm. So, let us look at the steps of processing for the depth buffer or z buffer algorithm. We have an initialization step where for all xy points the two buffers are initialized. The depth buffer or the zxy, you can either write it as zxy or depth xy depending upon your convenience. Depth xy is initialized to the maximum z value, okay, and this maximum z value is away from you, okay, is away from you, that is what you must visualize, and refresh buffer is assigned to a IB, which is which I will say it is a background intensity color. Now, there is an important point to be visualized here. your view direction could be along the positive z or negative z. There are two things which are usually used interchangeably, and it is important to take any one of these, because the back face culling algorithm computation becomes very easy, because you have to look into the sign of that c, which is the z component of the direction cosine of the surface normal of the polygon to compute a back face. After all the back faces have been removed, you just concentrate and work on the frontal faces to do the ZXY or any VSD algorithm. But for ZXY now, here we are talking of either a positive or negative z. Sign of the c for the back face culling could vary positive and negative depending upon whether you are looking positive z or negative z. But here also that is an important factor. When you are looking along positive z's, you must know that the faces which are close to you will have a small value of z, okay, and faces which are far away from you will have a larger value of z. That is, the z max will be numerically more than the minimum values of z which are closer to you. That is true. But when you are looking along negative z, just visualize negative z's, what will happen is numerically the surfaces which are larger away from you or farther away from you, in fact, will have a larger value of z in the negative direction. Larger value negative means smaller in the number scale, they will be lesser value, and that means surfaces which are closer to you will have smaller negative values, in fact they will be larger in that sense. So, larger and smaller numerically, if you take the absolute value in both cases, the z max will be larger, all right, but if you take numerically the algebraic difference and subtract one from the other and say from negative scale towards 0 towards positive, the values are increasing in this form. So, if you are looking along negative z, the z max values will be less if you are looking along negative z. Okay. You can look along negative z sitting along the positive, sitting somewhere along the on the positive z axis, you can look towards origin. That itself is a case of looking towards negative z. I repeat, think of an xyz coordinate system and you are sitting somewhere on the positive z axis. If you are looking towards the origin, your viewing direction itself is negative z. So, in that case, the farther values which are towards 0 are less values of z, but they are farther away from you, and values which are larger value of z, they are closer to you. Now, this is going to be different when your view direction changes to positive z. You could sit along negative z, you could sit on the negative z axis and look towards origin, or you could sit on the origin and look towards positive z axis. The situation differs, because here larger values of z will be farther away from you and smaller values of z will be closer to you. So, keep that in mind. I hope you are able to do the visualization of looking along positive z axis and negative z axis. Not only the back face culling condition of the sign of c changes, but this concept of z max numerically being higher or lower will change. I hope you are able to visualize that, because based on the concept or based on the way we are going to put the algorithm in terms of z max, looking along positive z direction and negative z direction, based on the method you choose for your viewing pipeline, viewing geometry and all that, the z max could vary, but you have to be consistent in your algorithm. You must not have today your algorithm picks up this, your algorithm tomorrow picks up positive z direction, things will do. So, we are assuming here that steps for the processing initializes for all xy the depth xy to a z max value, depending upon the negative z or positive z, which direction you are looking, the z max could be a large or a small value, whatever the case may be. Okay. Now, second step says that for each position on each polygon surface, that means you process polygon by polygon. So, if there are capital P number of polygons, you start with the first polygon, then the second polygon and so on, and what do you do for each polygon? This is what you do: calculate depth for each position xy on the polygon. Now, it is a polygon filling algorithm. You can always take a polygon in 3D, given the n sides or n vertices of the polygon, project that on the projection plane, which is the xy plane typically. You will get a polygon in 2D. Orthographic projection, mind you, just chop off the z values, neglect or omit the z values out, take the xi yi of the set of polygon vertices, you will have the 2D polygon. And When you have a polygon in 2D, you know how to fill it using a scanline algorithm. Use the same concept of 2D polygon filling, and what you get from 2D polygon filling algorithm? A set of xy points which are to be shaded, which are inside the polygon and which are for each scanline. So, we are talking of those set of xy points on the polygon in 2D for which the depth z for each position is known. Why it is known? You either it is known if it is on the vertex, or you need to calculate that. That is okay. The z point for each xy can be calculated, because that is the z which you have thrown out to get a point xy, of course for the vertices, but for each point on the polygon which is in a scanline, you can also calculate the z. We will see how. So, assuming that you know this calculation to be done, to obtain the depth z for each position xy on the polygon, you compare this z with the buffer value stored for the depth buffer or z buffer at the corresponding point x comma y, and find out if this z computed in this previous step big 1 here is less than the depth xy which has been initialized a priori or by the previous polygon processed. If that is less, then you do the following. You update the depth xy to the z value which is computed only when this condition occurs, and the refresh buffer xy which was probably assigned a background color at the initial stage, or it has an intensity of a polygon processed earlier, will have the surface intensity corresponding to that point xyz of the polygon. So, these are the simple 3 very qualitative steps of the z buffer algorithm. Of course, there is a lot of calculations which goes behind implementing these algorithms, but the conceptual it is very simple. Initialize, process polygon by polygon, and when you process each polygon by polygon, for each polygon scan through all the xy points, look into the z, compare the z value with whatever is stored in your depth xy. That is the comparison. We talked about depth sorting, comparing z. This is the step in the step number B2 which you have in the slide. We will see it again now. That is where you compare depth, and if the comparison succeeds based on a certain condition greater or less, it again depends upon where you are looking, positive or negative z direction, you update your depth buffer only at that point xy with the depth value or the, and as well as the refresh buffer with the distance intensity value. So, we look at the steps for processing. First step, initialize with the z max and the background intensity, and process polygon by polygon in step B, which has 2 parts. The first part of step B is calculate the depth value. We will look into these calculations today in the time remaining in the class today, and then when this depth value is found to be less than depth of xy for the depth buffer, this is the depth buffer, not this depth does not indicate the depth of the polygon. This z is the depth of the polygon, all right, but depth xy is the depth of the buffer which is used to implement a z buffer algorithm. Okay. So, in that case, if this comparison succeeds, otherwise do not do anything, but if the comparison succeeds, the depth xy is updated with the depth value, and the refresh buffer at that point xy is also updated with the intensity. So, this part of the computation of how to compute the IS, we will keep it pending till we have the still we discuss illumination and shading algorithms, but for the time being we know that there is a method to compute IS which is used to update the refresh buffer, and we have to only see how to compute the depth value. Okay. So, I hope the key ideas of the refresh buffer is what you have seen in this slide just now, is very initialize and process polygon by polygon. For each polygon compare depth and update the z, and based on the comparison update the zxy, and also if you are updating zxy, update the intensity refresh buffer also. So, IS is the projected intensity value of the surface at position x comma y, which has the minimum value of z at that current stage of iteration. So, this method of computing the intensity value at a position x y, we will discuss this later on, but this will be updated only when the zxy buffer is updated for a particular polygon. Now, the calculation of z, that is the most important part in this process. Let us look at the equation for a surface. We know we have seen this equation earlier when we talked about solid object modeling, and you can write the expression for the equation of a surface with direction cosines a b c as x plus by plus z, you know that, and henceforth you can write the expressions for z as this given here. Okay. So, the numerator divided by the denominator c. Now, if you see a, b, c and d are the coefficients of the surface which have to be computed a priori for a particular polygon, and then what you need to do is once you have the coefficients a, b, c and d with you, you basically need to substitute the value of x and y, compute the right hand side, that is how you compute z. So, the process of computing the value of z for a position x comma y on the projection plane involves the computation on the right hand side where the coefficients a, b, c and d are known to you, and then the x y value is picked up from the point on the raster buffer or on the projection plane, substitute on the right hand side, compute denominator by denominator term will give you the value of z. So, that is how you compute the value of z for a particular point, but there are problems in computing this value of z for the each particular point. All the set of points on the polygon will have different values of z in general, and if you need to repeat this calculation again and again for each particular point x y, you will be doing a lot of computations and that could be very costly. In fact, if you do that, we should say here that you are not exploiting the concepts of object edge and face coherence properties of polygon surfaces and scan lines to compute the value of z. Okay. So, let us look if we can use some method by which we can do incremental algorithm, some incremental values to be added to a previous value of z to get a new value of z. So, let us look at the equation of z for an x scan line. That is what we want. Okay. What do you mean by that? You remember the scan line polygon filling algorithm? In that, if you remember, we used edge coherence to get for the next scan line y plus 1 a value x prime which is x minus 1 by m. What was this m value? It was the slope of that line in 2D. Now, if you have an edge of a polygon in 2D, x1 y1 running from a point x1 y1 to a point x2 y2, we can calculate the slope m of that. Okay. So, that m in turn will help you to obtain that when you move from one scan line to another one, what is the next intersection of that scan line with the edge of the polygon. So, we did this computation and we use integer algorithm even to compute the next x prime for x. What does this mean in respect to the polygon in 3D? Let us say if you know somehow the z at the particular point x comma y here, say the left there are 3 dots which are marked here in this figure, and this figure says that this is a projection of a polygon in 3D on the 2D xy domain. And if it is so, for a particular point x comma y, if the z value is known, is it possible for us to compute the z value for the next point x plus 1 y, or even for the next scan line intersection with the polygon edge, which will be at some point, let us say x plus 1 y minus 1. Okay. So, this is now remember you can use these values of x and y at each of these points and use it to substitute it to the expression which we got z in the previous slide. We can use that for computation, but that computation will be enormous because you have to do that for each and every point x y on the polygon. So, we want to save time by see if we can simplify this calculation using some incremental logic. So, that is what we are concerned here, assuming that the z value is known at a point x comma y. Is it possible for us to compute the z value for the next point in the scan line, in the same scan line, or the next point in the next scan line, which is the intersection of a scan line y minus 1 with this edge of a polygon, which will be intersecting at x plus 1 or something else, that depends on the slope of the line. In fact, that 1 by m will dictate whether it will intersect at x or x plus 1. That you can find by 2D plan scan line polygon filling algorithm. So, but we are interested in z to compute the z value for each of these points. So, if we go back, the calculation of z is this which we want to avoid, and this next scan line polygon filling algorithm in 2D, which it will give you the next x prime intersection of the next x coordinate based on the slope of the line. So, if this is so, if this is the condition, that means we assume here that the z at this particular point x comma y is known, then from the previous expression of z, if we substitute z for x plus 1, I leave this calculation for you to come out that the z for the next x plus 1 will be given by this expression. Please try this calculation, it will be zx minus a plus c, and whereas for the net z y plus 1, you have to substitute y plus 1 for the next one, it will be basically z y with this x should be incremented by 1 by m, which will be this. So, these are the two calculations which I leave it to you for the exercise to compute and find out, and if you can get these calculations done, you can obtain the z value for the next point x plus 1 or for the next scan line using from the coefficients which are nothing but the direction cosines of the surface. A, C, B and the M are the parameters which are known for the from the 2D and the 3D properties of this polygon. If you look back into the slide once more, for a vertical edge, as you can see, the z prime will be z plus b by c, because the slope m will be infinity. So, this term will vanish. So, you know this is a special case only for a vertical edge, when the z value must be incremented by a value b by c. So, in fact, you have to remember just these three terms, a by c, b by c, a by m plus b by c. These are the three terms which will be necessary for you to implement the algorithm, which will be necessary to compute the z for the next point based on these three constants. Why these three constants are necessary? That is, given a z for a particular value x y for you, if you are interested to compute the depth of the next point x plus 1 or for the next scan line, which is an inclined edge or a vertical edge, these are the three cases for which you need to compute the z for the next point in the scan line if a current z is known to you. If that is the case, then you need these three constants which will help you to increment the z value based on these three conditions, which will help you to compute the next z value. So, we will stop with this particular slide here for the class today and continue henceforth in the next class from here on. So, to implement this algorithm, these three constants are required for each surface, and of course, keep thinking what is the special condition which will occur when c is equal to 0. Also, you should be able to find out these computations yourself, where how do you get these three constants which are necessary for your zx plus 1, that is the depth for the next point which is incremented by x, or for the next y coordinate which will be y plus 1 or y minus 1. In fact, you substitute this and get these constants out. You should remember that these are the three constants which are essential for you for this computation. So, we continue the next class from here, where we will see examples of how to do this, and also for a planar as well as for a curved surfaces here, and we will see how these three constants could be used very efficiently to compute the z for all the points in the polygon itself. Thank you very much. We will see you in the next class.